The next scenario we're going to focus on is the case of quasi-static adiabatic expansion. And so in contrast to case 1, which we detailed in the previous video, instead of being isothermal, we're now dealing with an adiabatic expansion. And so adiabatic means that there's no heat flow into or out of the system, and so as such, that's going to mean that our dq is going to be equal to 0. And so in the quasi-static adiabatic expansion, the process is still going very slowly, but essentially, for our gas expansion, what we have going on is that the gas is going to be expanding, so work will still be exerted by the gas, but there's not going to be any sort of heat flow going into or out of the system. All right? And so when we analyze our energy balance, so we have dE is equal to du plus dEk plus dEp is equal to dQ plus dW. We're still going to assume that changes in kinetic and potential energy are negligible, but we're also going to cross out dQ because this is adiabatic. And so what we're left with is that du is just equal to dW. All right, so that's just what the energy balance simplifies down to. From MEB2, if you remember, we know that the change in internal energy, or du, can be related to the change in temperature via this equation, right? Where N is the number of moles in the system, and CV is the heat capacity of the system. And I'm going to put a little tilde symbol on top of here to show that this heat capacity is going to be on a per mole basis. All right. All right, and we also have the derivative of temperature here. Okay. For dW, we could apply the same sort of analysis that we did in the previous video. So dW is equal to F gas dx, which we could relate to the pressure of the gas times the change in volume. And if we apply the ideal gas law, we could just plug in the ideal gas law for pressure. So we got dV over V. And so if we go back to our energy balance, for the du term, we have N, CV, constant volume heat capacity, times the derivative of temperature. And that's going to be equal to negative NR temperature dV over volume. Now, of course, the moles are going to cancel out, so we don't need to worry about the moles in the system. I do want to point out that the temperature here, in contrast to the previous scenario we detailed in the last video, the temperature that we're dealing with here is not a constant. Okay? So that temperature is going to be changing because as we expand the system. All right, and so to simplify the math out, what we'll do is we'll collect like terms on each side of the equal sign. So on the left-hand side, we're going to collect up all of the temperature terms. So CV over T dt. And on the right-hand side, we'll collect all the volume terms. Over V. Now, the gas constant's a constant, so I pulled it outside of the integral. CV here, though, this may or may not be a constant. You know, as you saw in MEB2, your heat capacity equation, especially when you're dealing with gases, that itself can be a function of temperature. And so for the general case, when you take the integral of all the temperature terms, the CV thing is also going to be a function of temperature. So that needs to stay inside of that integral. But to at least simplify the analysis, what I really just want to focus on is some general behaviors. And so for now, what we're going to do is we're going to assume that our constant volume heat capacity is just a constant. Okay? And so when we integrate this equation 3 over here, what we're going to get is CV times the natural log temperature 2 over temperature 1 is equal to the negative of the gas constant times the natural log of V2 over V1. Right? So we have natural logs on both sides of the equation. We'll play around more with this result later on, especially in Chapter 4. But for now, we could at least kind of gain some insight into how the temperature is changing as we expand or compress the system. And so if there's any expansion in the system, if V2 is greater than V1, if V2 is greater than V1, then this natural log term is going to be positive. But we have this negative sign over here, right? And so if V2 is greater than V1, the right-hand side of the equation is going to be negative. And if the right-hand side of the equation is negative, that means the left-hand side of the equation also needs to be negative. And for that to happen, since CV can't be negative, that means that our natural log term needs to be negative. And for that to happen, the T2 would have to be less than T1. And so if you have expansion during a quasi-static adiabatic process, your temperature is actually going to be lower in the final state than it was in the initial state. And if your system's undergoing compression, so V2 is less than V1, for compression, through the same sort of analysis, we would see that the temperature in our system would actually increase. So the system would get hotter if we compressed it during a quasi-static adiabatic expansion.